All right, so today we're going to keep talking about related rates, but we're going to move on to triangular things. These tend to be a little more challenging. And on all of these, or most of them, I am going to draw the diagram and probably have to do some side work to get everything we need for the problem. So for example 1, a water tank, which is an inverted cone, has a radius of 2 meters and height of 4 meters. If water is pumped in at a rate of 2 cubic meters per minute, find the rate at which the water level is rising when the water is 3 meters deep. Okay, so I'm going to draw an inverted cone. All right, and water is going into the cone. When you're given the radius of a cone, they're talking about the radius at the top. So the radius at the top is 2 meters, and the height of the cone from the vertex to the top is 4 meters. But that is going to change throughout the problem depending on where the water is. So if the water level is here, the water is going to have a different radius and a different height. All right, and so both of those are going to be getting larger as the cone gets filled. The height of the water, it gets larger, and the radius of the water gets larger. All right, so now let's write down what we're given. So we're given that the volume, the change in volume, is 2 cubic meters per minute. Now, I'm not going to write that we're given that the radius and the height are that, because that is actually changing throughout the problem. So we're just going to hold on to that information for now. All right, and then what we're going to find is the height of the water, how fast it's changing, dH dt, when the height is 3 meters. Okay, so this one involves some side work. So when we write our formula, the formula for the volume of a cone is V equals 1/3 R squared H. Now, we want to find dH dt. We're given dV dt. We don't know anything about dr dt. And so we can't solve it the way it's written right now, where we have a variable for R and a variable for H. It just will not work. So what we're going to do is do some side work. All right, so we're going to write a ratio. So cutting off where the water is forms similar triangles. And so the radius of the water over the height of the water is equal to the radius of the whole cone over the height of the whole cone. And then depending on what we're looking for or what we're given, we will either solve this for R or we will solve this for H. Now, because we are given the height and we want to find how the height is changing, we're going to solve it for R. So we're going to get rid of our R variable by multiplying by H. So on this cone, the radius is always going to be height, half of the height. Always, 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 no matter where the water level is. Now, one thing I want you guys to make a note is we always have to do some kind of ratio when we're doing a cone problem. So let's just say we must get down to one variable on cone problems. So that does require some extra work. But now that we know that R is equal to half of H, what we're going to do before we do the derivative is go and put 1/2 h in for r. So that means we are going to square it. When we square it, we're going to get 1/4 h squared times another h, which is going to be 1/12 h cubed. All right, so once we get down to just v equals something with only, oh, I left out the pi. Shoot. There's a pi in every one of these formulas. Okay, so now we are just down to v equals something with just one variable, just h. We're going to find the derivative. Okay. Now, what we are looking for is dh dt. So I'll take this equation and I'm going to solve it for dh dt by multiplying by 4 and then dividing by pi h squared. So dh dt is equal to 4 and then dv dt over pi h squared. Okay, now we're ready to plug everything in. Okay, so the height is changing at a rate of whatever 8 over 9 pi is in meters per minute. All right, well, let's talk about the ladder problems. Okay, so a 41-foot ladder is sliding down a vertical wall while its bottom slides away from the wall. So the top is sliding down, the bottom is sliding out. And it's sliding out at a rate of 4 feet per second. All right, how fast is the top moving when, that's the wrong no, that is the right sorry. It's 9 feet off the ground. Sorry, this is struggle today. All right, so we have a vertical wall and we have a horizontal floor. And on that, we have a ladder. And that ladder is always going to be 41 feet long. So I will go ahead and label it that way. The top is sliding down and the bottom is sliding away from the wall. So I'm going to just call this A, the wall side A, and the floor side B. All right, so what I know is that bottom slides away. So that's going to be dB dt at a rate of 4 feet per second. So because that B distance is actually getting larger, that is a positive rate because the B distance is getting larger. If it had someone was pushing it up against the wall and the B distance was getting smaller, then we would have that be a negative rate. All right, what we're going to find is dA dt when, when the top is 9 feet off the ground, so A equals 9 feet. All right, so this is the Pythagorean Theorem. And I don't care what 41 squared is, because when I find the I know it's a constant, and when I find the derivative of that, it's going to be 0. All right, and what I want to find is dA dt. So I'm going to solve it for dA dt by subtracting 2b dB dt. And dividing by 2a. Right, so what we have is dA dt is negative b dB dt over a. All right, so I'm ready to start plugging in. So this is where I'm going to have to do some more things. So I know what a is. A is 9. I know what dB dt is. That is 4. What I don't know is what b is, but I can figure it out. So that moment when the a is 9, sometimes I like to call that the magic moment. That's when we're trying to figure out what's happening. I know that b is 9 feet. I know that the ladder is 41 feet. What I need to find is, I know that a is 9 feet and the ladder is 41 feet. Well, I need to find b. So you might recognize that Pythagorean triple. It's not one that we use a whole lot, but 9, 40, 41 is a Pythagorean triple. So what I would do is go back and put I'm going to put 40 in for b. All right. So I have dA dt is going to be 40 times 4 divided by 9. So if you wanted to leave it as negative 160 over 9 feet per second, that would be okay. If you wanted to go ahead and write it as a decimal, that's fine. Also. All right, let's look at example 3. So a camera is mounted 3,000 feet from the space shuttle launching pad. The camera needs to pivot as the shuttle is launched. If the shuttle is rising vertically at 800 feet per second when it is 4,000 feet high, how fast is the angle of elevation of the camera changing at this moment in time? Okay, so let's draw the situation. This is another right triangle. So we're going to put the camera down here. Here's our space shuttle taking off. All right, and I know that the camera is 3,000 feet away. That is not going to change. That's a constant. But the space shuttle is moving up, so that height is changing. And the distance between the camera and the space shuttle is also changing. We may not need that, but that's okay. Yeah, we are going to need it. Okay, so let's write down what we're given. We are given that dH dt is 800 feet per second. We want to find, now this one is an angle, so we're going to use theta. D theta dt when h equals 800 feet per second. Shoot. I'm sorry. When h equals 4,000 feet. 8. Okay, now the thing that relates those, the height, and then the distance the camera's away, and the angle, is actually the tangent of theta. All right, so then when I go to find the derivative of this with respect to time, the derivative of tangent of theta is the secant squared of theta d theta dt. And then h over 3,000 is the same as 1/3000th times h. So that's going to be 1/3000th dh dt. All right, and then I want to solve that for d theta dt. So that means I'm going to divide by the secant squared of theta. So d theta dt is equal to, I'm just going to make this a little easier to look at. So dh dt over 3,000 secant squared of theta. All right, so really the only thing I need to plug in is dh dt, which I know is 800, and I need to plug in secant squared of theta. So I'm going to find what secant of theta is. So that's some more side work that I need to do. So secant is the reciprocal of the cosine, and the cosine is the adjacent over, the adjacent over the hypotenuse. And at the magic moment, I know that my adjacent is 3,000 feet. My opposite is 4,000 feet, because it tells us that in the problem. And that would make my hypotenuse be 5,000 feet. So then when I go to find the secant of theta, it's going to be hypotenuse over opposite. No, hypotenuse over adjacent. So 5,000 over 3,000, or 5 over 3. Okay, so d theta dt is equal to 800 over, let me figure out what this is real quick, 25 over 9 times, oh my goodness, times 3,000. So it looks like we're changing at 12 over 125 radians per second, or 0.096 radians per second. All right, let's look at 4. Suppose a man, 6 feet man, walks toward an 18-foot light pole at 1 foot per second. We want to find the rate at which the length of the shadow is changing, and then decide if the shadow is increasing or decreasing. All right, so we have an 18-foot pole. We have a 6-foot guy. $18 pole, 6-foot guy, and the ground. And shadow. Now, the pole isn't changing. It's always 18 feet. The guy isn't changing. His height isn't. But the shadow is changing. And the distance between the guy and the pole is changing. All right. So let's write what we're given. The guy's walking toward the pole. So that means his distance is decreasing. So we would say dt is negative 1 foot per second. We want to find how his shadow is changing, ds dt, and there is no wind, so it must be a constant change. Now we have another situation like the cone where we have similar triangles. So the little triangle, we have this length over this length, so that would be 6 over s. And then for the big triangle, this should be this length over this length. And that, it would be d plus s. All right, so that should equal 18 over d plus s. Now there's more than one way to set this up. When I did it earlier, I set up a little differently. So there's several ratios we could write. But to solve a ratio, you cross multiply. So we have 6d plus 6s equals 18s. All right, and then I'll just move my s's over. Now, since I want to find ds dt, I'm actually going to solve this one for s. So s is equal to 1/2 d. All right, so that makes it fairly simple now to find the derivative. So ds dt is 1/2 d dt. And the only thing we have to plug in is d dt, which is -1. So ds dt is equal to -1/2 feet per second. And the question is the shadow increasing or decreasing? That would be decreasing because we have a negative rate of change. Whew. Okay, a couple more. So a ship A is traveling due east, just kidding, due west toward Lighthouse Rock at a speed of 15 kilometers per hour. Ship B is traveling due north away from Lighthouse Rock at a speed of 10 kilometers per hour. Let x be the distance between ship A and Lighthouse Rock at time t, and y be the distance between ship B and Lighthouse Rock at time t. And they're shown in the figure. And this is a past AP test question that's been released. So A asks us to find the distance in kilometers between ship A and ship B when x is 4 and y is 3. So we're looking for this distance right here when we have 3 and 4. So that obviously is 5 kilometers, just using the Pythagorean Theorem. Okay, then we want to find the rate of change in kilometers per hour, the distance between the two ships when x is 4 and y is 3. So given dx dt is, okay, so this ship A is traveling toward the lighthouse, and so the distance is getting smaller, so this is a negative rate of change. And ship B is traveling away, so y is getting larger, so this is a positive rate of change. We're going to find d, and let's just call it r, dr dt when x equals 4 and kilometers y equals 3 kilometers. Okay, so this is the Pythagorean theorem. X squared plus y squared equals r squared. All of these things are changing, so we would find the derivative here. And we want to find dr dt. So we would solve that for dr dt by dividing by 2r. And I'm going to go ahead and divide through by that 2. You don't have to, I just like to do it. Okay, and then time to plug everything in. So r was 5 from the A part. Okay, so what we get is dr dt equals negative 6 kilometers per hour. So the distance between them is actually getting smaller at a rate of 6 kilometers per hour. All right, one more. This one is kind of rough. We have a lot of side work we have to do to make this work. So 2 cars leave an intersection simultaneously. One travels south at 18 miles per hour, the other travels west 22 miles per hour. How fast is the distance between them changing after 10 minutes? So our rates are all in miles per hour, and then it talks about minutes, so that's not very helpful. So let's just say that 10 minutes is 1/6 of an hour. And if you wanted to do that 1/6 as a decimal, you could, but you would have to go to a whole lot of decimal places. So it's a little bit better just to leave it in fraction form. Okay, so here's our intersection. One's going south, one is going west, and the distance between them is changing, but it does form a right triangle. All right, so I'm just going to call this ABC, and let's write what we're given. Okay, south one is B, so dB dt. Since that distance between the car and the intersection is getting larger, it's a positive rate of change. And then the west one is A, so dA dt. Again, we're traveling away, the distance between them is getting larger. We're going to find dC dt after, we'll just say when t equals 1/6 of an hour. Okay, so the relationship between these sides is the Pythagorean theorem. All of the things are changing, so we can go ahead and find the derivative. And we want to find dC dt, so this is very much like the one we just did. This is going to be slightly more difficult, but dC dt is going to be equal to A dA dt plus B dB dt over C. All those 2's cancel out. All right, here we go. We'll start plugging in, and we can't plug in very far, and we realize that we don't know anything. All we know is dA dt, but we need to know A, B, and C at the magic moment. We just know the time of the magic moment. What we need to know is the distances at the magic moment. So for A, we would take how fast this car is traveling and the amount of time the car has traveled. And that's going to give us the distance at the magic moment. And I'm going to just leave it as a fraction because it'll make it easier later. All right, and then B is traveling 18 miles per hour for 1/6 of an hour, so it's going to be 3 miles. And then C is the square root of 11 thirds squared plus 3 squared. And I'm going to go to all the decimal places. So you want to go to at least 5. Okay, so we can start plugging in. Okay, so I typed all this in the calculator and I got 28.425 and it would be in miles per hour. Okay, so sometimes you have a lot of side work to do to get all the things you have to plug in. Okay, so your assignment is to finish that worksheet from yesterday. So do the day 2 side. So it'll be 9 through 15.